All right, everybody, welcome back to Learning Calculus. I know it's been a long time, about 2 months, but I'm happy to be back. My voice just hasn't been working for so long. It hasn't been sounding, my voice has hurt a bunch. It's not been doing good. Today we're back with area, integration, and the accumulation of change. So it's a pretty big conceptual video. For a quick introduction and why I think I'm qualified to teach you some calculus, I think that math is fascinating. I took AP Calculus BC and I earned a 5 on the exam, which is equivalent to Calculus 1 and Calculus 2. And when I grow up, I hope to teach some sort of calculus or math when I grow up. I love teaching it. I love math. Always remember that the best way to improve at calculus, or for anything in that matter, the best way to improve it is by doing calculus work. Alrighty, so today's agenda. So first we're going to start off with understanding rates and what it means to accumulate something. It's pretty conceptual. I think it's relatively easy to understand just conceptually. And then we're going to understand finding area geometrically, and we're going to talk about the Riemann sums and trapezoidal sums. It's not necessarily a calculus concept, these two things, but it is still something that, at least for calculus AB and calculus BC, at least for those classes, you use Riemann sums. And we're going to go on to the definite integral. So just like we did with the derivative, we're going to have the definite definition of an integral, which is having a limit and stuff. And we're going to talk about integrals and the mean value theorem. We're going to talk about the fundamental theorem of calculus. And we're going to talk about some antiderivatives very briefly. So let's talk about the accumulation of change. So let's take a look at this quick example where a biker is biking at a constant rate of 10 miles per hour from 7 o'clock to 9 o'clock. And then we're asked, what is the total distance traveled by the biker? Now, if you're like me, I would just do a simple unit conversion. We're given that he's moving 10 miles per hour, and then we can multiply that by 2 hours. So 10 miles over hours times 2 hours, the hour units will cancel out and you'll be left with miles as your unit. And then when you do 10 times 2, it's obviously 20. So you travel 20 miles. Pretty easy to think about. But you can also think about it like an area. You can think about it like an area underneath a curve. For instance, this is the rate of 10 miles per hour plugged into Desmos. As you can see, it's just a line. And if you were to think about it like area underneath this curve, if you calculated this rectangle right here that you can see me circling out with my little laser pointer, if you were to do the x width, which is 2, and then the y width, which is 10 times 2 is also 20. So you can think about it like area. And the key takeaway is that area underneath a curve accumulates the change of a rate. And also area is an accumulation of something. That's the main takeaway. One thing that's really important, that's kind of an aside that I should have mentioned in the slides, but I didn't, is that when people think of when they think of integrals, they think of area. That's not the correct thing to think about. When you think about an integral, you should be thinking about the accumulation of something, because fundamentally that's what an integral is. It's the accumulation of something. So anyways, that's just a quick important takeaway. Like I said, especially in AP Calculus AB and BC, you will be sometimes asked to find the area of curves geometrically. So it's nice to just remember your area equations. You have the area of a rectangle, length times width, area of a triangle. Obviously, I don't need to go over all of these. Area of a trapezoid, I highlighted in green because we will be coming back to it later when we talk about trapezoidal sums. Calculating area underneath a curve can be done geometrically. So like I said, in AP Calculus AB and BC, you may be sometimes even given a FRQ. That's like, find the integral of this function, but it doesn't give you a function, right? You do it geometrically. So let's talk about Riemann sums, or they're also called the rectangular approximation method, or RAM. You can hear people say. The key idea is that you can use rectangles to approximate area, and the more rectangles you use, the more accurate that approximation is. So I believe, yes, I have an example problem right here. I'm not going to go over it in total depth. Basically, the idea is that this ball is falling, we're given its acceleration, and then we're just given it as data points. So we're not given a function of its acceleration, we're given data points. But using the data points, we can use some basic math. We can use a rectangular approximation method to find the area underneath that curve and to find, for instance, the speed that something happens. Because that's what would be, if you're accumulating area, that would be equal to its velocity. You're accumulating speed, basically. So, for example, when doing the left Riemann sum, so the left rectangular approximation, that's what I'm saying is L sum. You use the points at their left-hand value. So, for example, we have, does it say? It doesn't say. We just have 1, 2, 3, 4, 5 splits of data. And basically, when you're using the left-hand side, think of these brackets. Always use the left side of the bracket. So, for example, 0.2 times 1 minus 0. The idea here is that you have a acceleration of 0.2 for 1 second, because that's how long that 0.2 is being calculated for. But if you were to do a right approximation, you would have a speed of 1 for you would have a rate of 0.23 for 1 second. So that's kind of the difference here, that you're using the right method versus the left method. And that goes for all of these different things. Basically, the idea is that you multiply your function's value. So like, if you have a function a of t that you have data points for, you multiply a of t by how long t is. You take the end point minus the beginning point, right? 1 minus 0, 4.5 minus 4. So you can see how that's working out here. Trapezoid sums are another thing. Once again, my experiences with AP Calculus. So AP Calculus does do trapezoid sums. It's just a more accurate version. So, yeah, you just average the two heights, and then it's being multiplied by the width of the rectangle you're doing. So that's what this looks like right here. So the area is equal to this, and that's the average height of the function. Okay, so Riemann sums are kind of lame, right? You might have been, your eyes, I don't know about you, but my eyes were kind of glazing over when I'm talking about Riemann sums, because this is a calculus video, and this is for a calculus class, but none of what we've done so far is calculus. So now let's turn this into calculus. As mentioned before, the more rectangles that you use in a Riemann sum, the more accurate your approximation becomes. That's a really important thing for Riemann sums, and that's where the integration comes in. So we're gonna do some quick notation right here. N is the number of rectangles. Delta x is the difference in x, and then f of x is the height of the rectangle. So it's the height of the function. And we're going to have this right here. This is the formula basically for a Riemann sum. So you have, it might be a long time since you've seen sigmas and stuff, because, you don't really see them that much. But in calculus, you'll start seeing them all of the time. We have the summation when k equals 0, or sorry, k equals 1. That just basically means like, don't worry about this part. Just worry about n. Worry about this right here. This is basically just area. You have the function, which is the height, as you can see right here. The function is the height, and then delta x is the distance between these two rectangles. So kind of just like we did with the derivative, we're going to make something approach infinity. So we can use a limit and say that the n, so the number of rectangles, sorry, that's supposed to say rectangles. As the number of rectangles approaches infinity, your summation will look like this. And this is what an integral is. So congratulations, this is the definite limit definition of an integral. You have the limit as the number of rectangles approaches infinity of the summation of that rectangle's area. You can rewrite it though. So we say the integral from a to b of f of x with respect to x, or dx. So this is, congratulations, the definite integral. Basically what this is saying is the s is, fun fact, is a long s. That is what the integral sign is. It's just a stretched out s, and it stands for sum. You're summing up little tiny rectangles because dx represents an infinitely small size. As you can see right here, dx is what we call a differential. It's an infinitely small amount of change. So you're taking the function and you're multiplying it by an infinitely small amount of change across the interval a to b. As a quick aside, area is normally a positive number, but integrals can be negative. This is because you are accumulating change, not calculating area. So that, once again, that kind of connects back to that thing that I mentioned at the beginning of the video. Integrals accumulate change, not area. Because, like, for example, you can accumulate debt. That is accumulating negative money, right? Negative money, it's not area. You can have negative integrals, if that makes sense. So to keep on going on with definite integrals, to find the area, let's take a look at this. It's a triangle, and you're going to find the area from -3 to 3, so from here to here. This is an absolute value function, and you would say the integral from -3 to 3 of the negative absolute value of x plus 3. And when you do that, you can find it geometrically, and you can find that the area underneath this curve is equal to 9. This is just a rectangle with a base width of 6 and a height of 3. So it's just a triangle. Once again, as I mentioned, definite integrals on the AP test will sometimes just straight up be geometric area. You won't be given a function. You won't be doing, all you'll be doing is just finding area geometrically. Okay, let's talk about some properties of definite integrals. So for number 1 in this blue box, we have the constant multiple property. Like with most things in math, if you have a constant being multiplied by something, just pull that constant out, pull it out to the front. It makes problems easier if you don't have to worry about that function or that constant. B is called the reversal of limits property. So this is an interesting property. If you have the integral from a to b of the function f of x, it's the same as the negative integral from b to a. As I mentioned on this slide, you can have a negative integral, right? You can have negative accumulation. So with the reversal of limits property, sometimes it might be smart to solve your problem by reversing the limits, right? You can just say the negative integral is equal to the reversed limits, because instead of accumulating area, you can kind of think of it like you're deaccumulating area, right? Instead of accumulating f of x from a to b, you can deaccumulate f of x from b to a, if that makes sense. So yeah, that's why that negative is out there. This cyan is called the additive property of integrals. Once again, pretty simple. If you have two different functions that you're integrating, you can just split those integrals up. You don't have to integrate them both at the same time if they're just being added or subtracted. The zero width interval. So as I've mentioned, integrals function based off of this little dx, right? The differential, which is an infinitely small rate it's an infinitely small amount of change. But if the interval you're accumulating is 0, there's no way to have a dx. You can't have an infinite, it's an infinitely small amount of change, but it's not a zero amount of change, if that makes sense. So if you have the same interval, then you can't accumulate anything. Your answer is 0. And finally, the additive interval property. This one is really interesting, actually. It's pretty common, at least in AP Calculus. You can see it on FRQ sometimes, where if you have a function a to b, if it makes sense to do so, you can split up the integral and accumulate it to one variable. So you can say from a to c, and then you can add the integral from c to b. So, for instance, it might be useful to do that if you're calculating like geometrically, if the integral changes shape. So like if it goes from a semicircle to becoming a line, it might be smart to break that integral apart into so find the area of the semicircle and then add the area of the line, if that makes sense. These are pretty self-explanatory. I wouldn't worry about them too much. They're pretty easy to remember. Let's briefly talk about the average value of integrals. So if you have the area and the width of a rectangle, dividing area by the width will give you the height. So for instance, you could say a rectangle has a width of 3 and an area of 12. So you can find that height is equal to area divided by width, which is equal to 4. But if the shape has a curvy top, area divided by width will instead give you the average height of the top of the shape. So that's what this is saying. This is the average value of a function across an interval a to b. So right here what we have, so a to b is the width, or b to a is the width of the interval. It's, just the end value minus the start value. The integral is the area. So you have area divided by width. And it gives the average height of the function. Alrighty, so now that we've introduced integrals and we've introduced derivatives, they're the two main branches of calculus. Let's finally connect the two ideas in what we call the fundamental theorem of calculus. So this is where calculus starts becoming really cool, because we've learned about derivatives, which is the rate of change, right? And now we are learning about integrals, which is the accumulation of change. And through the fundamental theorem of calculus, this shows us how they are connected to each other. So let's go over, this is the explanation that made most sense to me. So let's talk about where the fundamental theorem of calculus comes from. It's pretty conceptually, it's kind of difficult to wrap your head around. But if you say that, so let's connect back to the integral of a function is given by this summation. And let's call that integral a function capital F of x, where capital F of x is just the terms f of x times dx, and it's being added together. So this is what capital F of x looks like. This is what it looks like written out. So you have f of x1 times dx plus f of x2 times dx plus, you're adding these infinite amount of terms together. F of x has a very, very interesting property in that it is directly rated to f of x, lowercase f of x, which is the function that you are integrating. So the integral increases by f of x plus dx, so you add a little bit of change, times dx for every single increase in change. So it can be written in a statement like so. So this is what you're saying. So f of x increases by f of x plus dx times dx. So once again, for every increase in dx, f of x increases by lowercase f of x plus dx times dx, if that makes sense. I think it's easier to look at what it's written like instead of me saying it. This is what you're saying right here. Okay, so here's the big moment. So as we went over, capital F of x increases by this for every single increase in dx. If you resolve this equation and you solve for f of x plus dx, so a little tiny accumulation of change, you find that this is just a derivative of the function capital F of x, right? We have the original function plus a little bit of change, dx, minus the original function, divided by that little tiny amount of change. That's literally the definition of a derivative. Remember, you have f of x plus h minus f of x divided by h, and there h is approaching 0. So in other words, the derivative of an integral is just the function you are integrating. So this, I even highlighted it. I don't highlight anything. I make it a different color when it's important, but I highlighted this because that implies what the fundamental theorem of calculus, which is stating that the inverse operation of a derivative is integration, and that the inverse operation of integration is derivatives. So here's the official definition for the first part of the fundamental theorem of calculus. It says that if f is continuous on a to b, the function capital F of x equals the integral from a to b, f of t dt. It has a derivative at every point on the interval, and then the derivative of this integral function is equal to this right here. And then that's equal to f of x. So I'm not going to say that all out. What this implies, it implies three things. 1, every continuous function has a derivative. 2, every continuous function has an integral. And then number 3, integration and differentiation are inverse processes of each other. So they cancel each other out. As you can see, that's happening right here, where you have the integral of the derivative is just equal to the original function. That's what's happening right there. And then here's the second part of the fundamental theorem of calculus. If f is continuous at every point a to b, then capital F is the antiderivative of f, then the integral of lowercase f of x is equal to the antiderivative of b minus the antiderivative of a. So this theorem of calculus is super important because it tells you how to solve definite integrals. You can see in blue what you have to do to solve a definite integral is you calculate the antiderivative, and then you find the change between the top bound and the bottom bound. So, as we've discussed, integration or finding area is the accumulation of rates of change. We've also discussed that derivatives represent the rate of change. So if you were to reverse a derivative, that process is what integrals use to accumulate area. So that's how integrals work. It works with the antiderivative. And yeah, this is kind of just restating. States that the relationship between accumulation and instantaneous rate of change, they are opposite processes of each other. If we're asked to find the area underneath a curve, it can be done geometrically, or you can use anti-differentiation. So now let's move on to antiderivatives. So here we go. It says, let's find the area underneath the curve x squared on the interval 0 to 3. So based on the second fundamental theorem of calculus, we know that if we need to find the area underneath a curve, what we can do is we can calculate the antiderivative of your function and just evaluate it at the endpoints, right? So we have our function x squared. Let's find the antiderivative of that. So let's think about it really quickly. And don't look at this. This tells you the answer. If you were to think about it, you have a little polynomial right here. If you were to take the derivative of that, what you would do is you would use the power rule, right? You subtract 1 from the power, multiply the front by the original power. You could say like you drop down the power, subtract 1 from the power, if that makes sense. The reverse power rule then would state that you add 1 to the power And then using that new power, you divide the original polynomial part, like, the original term. So let's do that right here. If we take x squared and we add 1 to the power, so it becomes x cubed, and then we divide it by the new power. So x cubed divided by 3, congratulations, that's the antiderivative of x squared. You could also say that that is the you can say that that's the antiderivative. You could say that's the integral of x squared. And really quickly, just to verify, if we were to take the derivative of this function, we would use the power rule. The normal power rule states that we take 3, we multiply it in front, and then we subtract 1 from the power. So this 3 becomes 2, and then we have 3x to the power of 2 divided by 3. The 3's cancel out, and you're left with x squared. So yes, this is the antiderivative. Congrats. And then once again, by using the second fundamental theorem of calculus, you can say that the derivative at the top endpoint minus the derivative at the bottom endpoint is equal to the area underneath the curve, which is 9. And yeah, that's the integral of x squared from the interval 0 to 3. So the area underneath the curve from here to here, this area is 9, which is pretty cool to think about. Alrighty, so to end out this video, let's talk about basic integration rules. So if you have the integral of 0 dx, it's equal to a constant c. Because if you were to think about taking the derivative of any constant, if you were to take the derivative of c, you would just have 0. So the integral of it would obviously just be a constant. If you were to have the integral of 1, so you have a constant, you would have x plus c. You would have x, and then you would have a random arbitrary constant. If you had the integral of k, where k is any constant, you would just have k times x plus c. And if you had the integral of this, so you had the integral of x to the power of n, where the power is a number, you have this. This is the reverse power rule. It's x to the power of n plus 1 divided by n plus 1. So you add 1 to the power, divide by the new power, if that makes sense. And you add an arbitrary constant c. So once again, the reason why this plus c always pops up is because when taking derivatives, any constant becomes 0. So when you're taking integrals, we do not know that if a constant was derived, so we just represent any constant with the variable c. So c can be any real number, so it could be like 0.5, it could be 15, it can be 20 billion. But c is, c is what we use to make sure that we are representing the antiderivative property properly, because once again, you could have some constant that you take the derivative of, and it just goes away. And then when you integrate that, you have no idea if there was a constant there. So yeah, don't forget plus c. This is a little meme showing that. Don't forget your plus c's. Plus c's always happen. Alrighty, and then here's the basic integration rules for trigonometry derivatives. It's, basically the same as if you know derivatives, you should know these. Pretty self-explanatory. It's just reverse, right? Sine of x becomes cosine. But then when you take the integral of cosine, it becomes sine. When you take the derivative, or when you take the integral of sine, it becomes negative cosine, right? You're just doing the opposite of taking the derivative. The integral of 1 over x, this is an interesting one, is equal to the natural log of absolute value x plus c. So, obviously that's because we know that the derivative of the natural log is 1 over x. So the integral of that would be the absolute value of x. And the reason why the absolute value is there, I don't know fully how to explain it, but it's because of you would have to separate it into piecewise functions. The idea is that you have the absolute value because you can't have the natural log of a negative number, right? If you put a log of -1, that wouldn't make sense. So yeah, that's why the absolute value is there. because you can't have the integrals of negative numbers. So the absolute value is there to make sure that you can actually, calculate the thing when it's the natural log. Because once again, logs can't be negative numbers. Integrals of exponential functions, pretty easy. E to the x, this one, all of these. These are all pretty important. I would just remember them. They're not that hard to understand, though. So, although it might be easy to remember integration as area, you are not directly calculating area. You can calculate area, and for instance, especially once you start getting into like volume of revolved circles or like stuff like that, like when you revolve something around the x-axis, yeah, you're calculating area, but you're not always calculating area, right? You are accumulating a change in f of x. Sorry about that. You're accumulating a change in f of x along x, which we call dx. Like you're accumulating little bits of dx, little infinitesimally small changes of x. That's what dx is. This is just like a final reminder. It's, really important. I remember plenty of people in my calculus class were very confused about, they were confused about the fact that it's an accumulation of change. So, I hope that was helpful. The main thing, I would say, once again, integrals are the accumulation of change. Fundamental theorem of calculus, very important to remember. These are pretty important to remember. I would remember these. Overall, though, yeah, this video is kind of difficult because it's a lot more conceptual rather than like actually solving stuff. The next video is going to be about integration methods, so that's going to be fun. Integration methods, I like them, they're fun. It's just going to be a bunch of practice problems next episode. So yeah, but today was once again kind of more of like a discovery of the integral, right? We did the same with the derivative. You kind of discovered what it was. So yeah, anyways, thank you guys very much for watching, and yeah,